Okay, welcome to Ions and Solutions and Colligative Properties. This is a summary of Chapter 13 with some level of detail. This will be a presentation that'll be broken up into three parts. Section 1, this is only a two-section chapter, but Section 1 I'm going to break up into two kind of mini parts, if you will. Roughly, like 20 slides or so each, which include solutions to some in presentation problems. We have already covered, before the COVID-19 break from school, we've already covered most of this section, so I'm going to review this relatively quickly. But it is a video, so you can stop, pause, go back, rewind, mute the volume if you want, and just watch this. Take a look at your notes, whatever you need to do, and of course, always read the chapter. There is always an encouragement to take notes while you're doing this, take notes while you're reading, and here we go. Okay, you already have the student learning map, and it should already be filled out, at least in part. Do realize that your unit essential question will be on the Chapter 12-13 combined test, which will not be long out from now. And here is the Section 1 lesson question, and you should already have that. But if not, pause and write it down and think about the question itself and the potential answers. Okay, this gets into basically ions in solution, and to talk about ions in solution, we talk about dissociation. Dissociation is the act of ionic compounds dissolving and the ions themselves being split apart from each other into free ions that are then surrounded by the solvent. Most of the time that is called solvated or hydrated, depending on if the solvent is water. This is a particle view. Remember, we're very big into particle models, and we talk about them quite often. I should have you draw them more, sketch them more, but here is an example of a particle model of sodium chloride, regular old table salt, in a dissociated state in water. And you see the labeling, and this is most likely a diagram out of your text. Okay, 13.1, dissociation. There's a vocabulary term again, separation of ions when soluble ionic compounds dissolve. This is showing sodium chloride dissolving in water, where you have sodium chloride existing as a solid, dissolving in water, so I'm just going to put the solvent above the arrow, and water, through its polar covalent action of attraction to the ions, is able to pull apart the sodium ion and the chloride ion. They stay ions, but now notice that they are aqueous, to remind you, kind of get back into the mode of thinking here. And as it turns out, that for every one piece, if you will, of sodium chloride that we dissolve as a solid in water, you'll get one sodium ion and one chloride ion floating around in solution, surrounded and stabilized by the water molecules. And therefore, we can extend the idea that if you had 1 mole of this dissolving, you would make 1 mole of sodium ions and 1 mole of chloride ions. Notice when an ionic substance dissolves, you always make more ions than you actually dissolved because it splits apart. So 1 mole actually creates 2 moles in solution. This concept will be important later on, and I want to remind you that you heard it here, you heard it now. Here's calcium chloride, a different type of salt, and this is most often ice melt, if you will, a pretty popular product. It's not really food grade, and it's less expensive often than sodium chloride. Here, when you have 1 mole dissolving, it'll split up into calcium and chloride ions, but notice for every 1 calcium you get 2 chloride ions splitting apart. Now these are separate from each other, so that's why even though over here it's a subscript, because it's in a compound and it's a solid, over here each of the chloride ions are going to be separated. And so that's why the 2 comes out front of the chloride, indicating 2 independent chloride ions floating around. And of course we have the mole ratio down here, and notice the change in state. They are now aqueous. And we are assuming that 100% of whatever we put in will break up completely into these ions, and so that's called 100% dissociation, and we assume that. And for any substance that is highly soluble, we're really close to 100%. Okay, considering then if we had ammonium chloride, sodium sulfide, and barium nitrate, and we dissolved write a dissociation equation for, like up here, and also kind of with the ratios that we have going on in this area, I've also given the ability down here to write ratios. I know we already worked these in our class, and so here are the answers that we generated during that time period. You can pause and look at this more closely if you want. I'm going to move on. Okay, precipitate. Now remember that you'll need to get a copy of the solubility rules. If you do not have them, you can most likely find them in the Google Classroom, linking over to the Google Drive and going into the Chapter 13 folder. And you'll find a lot of material in there, including, I think, a copy of this presentation if you're getting this off of YouTube and not out of the Google Drive. So anyway, with solubility rules, we're going to want to keep them handy, because for anything that is soluble, that is ionic, we want to be able to look up on that solubility rule list and find out exactly what is soluble and what is not soluble. And now we have an example down here. I believe we worked this out as well. All states of matter for ammonium sulfide reacting with cadmium 2 nitrate, and both of these are aqueous, both of these are soluble. So this is what we came up with, in the fact that as they react together, we have ammonium nitrate forming and we have cadmium sulfide forming. Cadmium sulfide is insoluble in water, and so I've highlighted it here as a soluble, or as a solid rather, and this means that it's a precipitate, so a precipitate has formed. Okay, this brought us to what we were calling overall or full ionic equations. And it will show all soluble ions dissociated. I think that's an orange color, but you know me in color. And then all liquid or solid or gas chemicals, which will stay intact as molecules or molecular solids, or molecular substances, I should say, because they're not all solids, would be indicated there. So I've put all of the arrows down here color-coded, indicating that everything is aqueous except then cadmium sulfide. The cadmium sulfide is our precipitate. It is insoluble. Of course, then, if we eliminate all of what are called the spectator ions, these are ions that exist on both sides of the arrow, and they are unchanged. So they are aqueous before they started, they are aqueous after they started, and they are the exact same ions. We call them spectator ions. They simply do not take part in the chemical reaction at all. They do nothing but float around in solution, if you will. And so by eliminating the spectator ions, that gets us to the net ionic equation. And the net ionic equations are very interesting in that they really show the chemistry that happened. So in this particular case, we have the sulfide ion. It was aqueous. It reacted with the cadmium ion. It was also aqueous, and when they reacted together, they formed a solid cadmium sulfide that precipitated out, and water, being polar covalent, still was unable to break this bond once it formed, because that bond is very strong. That's what makes it insoluble in a substance like water. Okay, net ionic equations. When can we write them? Well, these are 5 different instances when a net ionic equation would be possible. When non-ionic become ions as products. When ionic become non-ionic products. When a phase change occurs, something like, just became a solid in that previous example. If water forms as a product. When a precipitate or a gas forms, and there are certainly other instances, but these are the main ones. What tools do you need to write net ionic equations? You need to have the ability to predict products, of course, for synthesis, decomp, single and double replacement reactions. We won't bother with combustion at this time. We need potentially the reaction templates there, the prediction templates that you have. You would need an activity series if it is a single replacement reaction. And of course, always start with a balanced equation, just like in stoichiometry. Good idea to have solubility guidelines so you can predict all states of matter, solid, aqueous, etc. Okay, so we should have tried these in class. We might have gotten this far. We may have gotten farther. So what do we have? Will a precipitate form of solutions of potassium sulfate, barium nitrate? Will it form if they combine? And if so, then please write a net ionic equation. Also, it's the same question for a reaction of 2 different reactants down below, potassium nitrate and magnesium sulfate. Assuming we worked these in class, I will skip to the answer. So that should be next slide. Okay, here we are with the next slide showing the reaction of potassium sulfate, barium nitrate. Both are soluble, both are aqueous in this case. Reacting to form potassium nitrate, according to my solubility tables, is soluble, so it's aqueous. And barium sulfate, which is a solid, it is insoluble in water. I have taken all of my substances, I have broken them up as reactants, as ions, so I have dissociated them. They are all aqueous. Here's my arrow. One of my products remains aqueous and ionic, and so here we are there broken up, but the barium sulfate stays, if you will, molecular, even though we would call it an ionic substance, Ba with the 2 positive, SO4 with the 2 negative, and write the formula. We're going to treat it as a molecular solid for this instance. And so then, going back through, I eliminate what I have underlined as the spectator ions. What remains is my net ionic equation, which, by the way, does balance. It self-balances, but all net ionic equations should balance just like everything else. Okay, let's move on to the second example. Now, the second example had potassium nitrate reacting with magnesium sulfate, again, both aqueous, forming potassium sulfate. Anything with potassium is always soluble, and so this is. And magnesium nitrate. Anything with a nitrate is soluble, so this is soluble. So everything is aqueous. I can do a full or a complete ionic equation. Even the products are going to be broken up into ions, and so dissociated completely. But down here, since all are spectator ions, there is no net ionic equation possible for this reaction. If this is the case, no reaction technically has occurred. We talked a long time ago that when we have double replacement reactions like what this is, that not all double replacement reactions actually occur. We treated them as if they would all occur, but they don't always. How do we know? This is one instance. When there is no phase change, when there is no possible net ionic equation, this reaction, while we can predict it, actually will not occur because there's no way to prove that your products ever combine together because they always stayed apart from each other. So, just a little information there for you. Moving on. Okay, here we have a couple of more examples. One, number 3, I guess, in the series. We have a reaction, barium chloride, sodium sulfate. If a precipitate forms, looking for a net ionic equation, and in this case, also identifying the spectator ions as a separate question. And then in number 4, it's just kind of a modification and an abbreviation of this type of a process, and it's just cutting to the chase. Write the net ionic equation for the precipitation of nickel 2 sulfide. Okay, so I don't know if we worked these or not, but I believe you have the process, so I'm just going to skip to the answer. So here's number 3. Okay, with number 3, barium chloride is aqueous. Anything with chlorine pretty much is aqueous. There are a few exceptions. Check those on occasion. Sodium sulfate, anything with sodium, no exceptions, is always aqueous, so there we are. And that'll form barium sulfate and sodium chloride. Sodium chloride, very aqueous, very soluble rather, so it's aqueous. Barium sulfate is insoluble, so there's my solid. I can break everything up as reactants, dissociate them, show them as ions, making sure, again, they're balanced, and making sure that subscript comes out as coefficients, because these are separated ions. Arrow, barium sulfate, again, a molecular solid, and then sodium and chlorine broken up. I've underlined my spectator ions, so I can now identify them, so here they are. And then what remains is my net ionic equation. Now, the barium and the sulfate, it doesn't really matter what order you write them down here, only that the order of them in the molecule is actually correct. Then you're good to go and make sure it balances. Okay, moving on to number 4, which is a nice modification. It really abbreviates the question. So let's check number 4 out. Okay, so number 4. To write a net ionic equation for a precipitate, often abbreviated lowercase ppt, it's not always necessary to know what the spectator ions are, so we just don't need to know them. So it's possible to write net ionic equations for the precipitate of, in this case, nickel 2 sulfide, which is insoluble. So what do we have? Well, if it were soluble, nickel 2 is aqueous starting out, combining with sulfide, which would be aqueous starting out, and that would form nickel 2 sulfide here as a molecular solid. That's the net ionic equation. I don't need to know the spectator ions and its balance, so it's right good to go. Now, check this kind of addendum down here. How did nickel 2 come to be in solution? Honestly, I don't know. But what I can say is it must have been ionically bonded to some anion that allows for Ni whatever, NIeq, to be soluble, such as the example nickel 2 chloride, which would be soluble. The same can be said for the sulfur ion, the sulfide ion. We don't know what it was bonded to, but it must have been some cation that allowed for the sulfur to actually be soluble as a reactant. And so whatever XS is, ammonium sulfide would be a good example, sodium sulfide would be a good example, and so on and so forth. So we can write net ionic equations and never have to know the spectator ions. Interesting. I like that. Okay, moving on. Okay, it looks like we are drawing to a close on this part 1. This was a quick review, maybe not as quick as you would like, but it was a fairly quick review of the initial part of section 1, which focused on first dissociation, understanding how ions simply are split apart in solution as they dissolve and exist as free ions. That was an important concept. Also, the other concept is about being able to write ionic equations, the full or complete ionic equation, and identifying spectator ions, and identifying and writing the net ionic equations whenever possible. Okay, so of course we're looking at the student learning map again, main unit essential question, and that's kind of my visual indicator, as well as this, that we are now moving on to part 2, a different video, but part 2 where we will look at the ionization of molecular compounds, because it's going to be a molecule now, where is it, molecule, that there are no ions there. That's a molecule. Those are all covalently bonded, but some covalently bonded substances can ionize, and by ionization that means that they will produce ions in solution even though no ions existed before. I would strongly recommend you read chapter 13, the rest of section 1, go all the way to section 2 if you want, before you read the video or listen to the videos, watch the videos, and take notes. Please take notes. Pause, mute the volume, do whatever you want to do, but take notes and kind of keep in tune with this, even though all tests from here on out are kind of open note, open book. There's no way to control that otherwise. Nice to have your resources, but you still have to understand what you're doing. Okay, so I believe this is the end of the entire presentation for this particular part. 13.1 will continue in part 2, and then part 3 will exclusively be about colligative properties, which is section 2 of chapter 13. Thank you.